Arkansas, Physics and Human Affairs, Lecture 14, The Nucleus and Radioactivity for April 14th, 2020. Don't forget the lecture quiz posted to the lecture quizzes section on Blackboard due tonight, that is Tuesday, April 14th at 11:59 p.m. Please take notes on this lecture. Pause the video, go get your notebook, I'll wait. So let us begin now, as we usually do, with poetry. Say it with me. Every particle has uncertainty, so I have to make a decision. I can either know its velocity or I can know its position. When I say physics, you say rocks. Physics! Did you say it? Yeah, you did. When you put gasoline in your car or coal in your power plant or natural gas in your stove, in other words, when you extract energy by burning something, you are converting chemical energy to whatever form of energy you need. In a chemical reaction like combustion, you are taking energy from the electrons surrounding the nucleus of the atom. And there's a fair amount of energy to be taken from electrons. You can use chemical energy to power homes and cars, even cities. But the amount of energy in the electron cloud surrounding the nucleus is nothing compared to the amount of energy in the nucleus itself. In other words, chemical energy is child's play compared to nuclear energy. Before we dive into nuclear energy, we need to introduce a new particle, the quark. This image shows a diagram of, this is not a subatomic particle. This is the fictional character Quark from Star Trek Deep Space Nine. He will do anything for you for a price. In nuclear physics, quarks are what protons and neutrons are made of. Quarks are classified by generation, which has nothing to do with parents and children, and by flavor, which has nothing to do with the human sense of taste. You can think of the 6 flavors of quarks by dating app. Okay, the first generation quarks are called up and down, like Tinder, swipe right, swipe left, kind of mean thumbs up and thumbs down, right? If you're on FetLife, you might be looking for a second generation quark, a charm quark, or a strange quark. And if you're on Grindr, you might be looking for a top quark or a bottom quark. I really do want to keep this job. It comes with healthcare and everything. There are no versatile quarks in nuclear physics. Okay, so particle accelerators are these laboratories where you smash atomic nuclei together at near light speed and just see what comes out. When you do this, you often get lots and lots of quarks, all generations of quarks. However, second and third generation quarks are very unstable. They decay very quickly into first generation quarks. So in nature, almost all quarks are first generation quarks, that is, up quarks or down quarks. If a quark is all by itself, not bound to any other quark, we call it a naked quark. And quarks do not like to be naked. They very quickly find other quarks to hook up with, and they usually hook up in groups of 3. An up quark, a down quark, and some third quark that may be up or down. So the most common combinations are up, up, down, and up, down, down. These 2 combinations are better known as protons and neutrons. A proton consists of 2 ups and a down quark, while a neutron consists of an up and 2 down quarks. So let's revisit the structure of an atom. An atom consists of a nucleus that may be surrounded by a cloud of electrons. That nucleus consists of protons and neutrons. The proton consists of 2 up quarks and a down quark, while a neutron consists of 1 up quark and 2 down quarks. Recall that in the electric force, like charges repel. The diagram here shows a helium nucleus with 2 protons and 2 neutrons. Those neutrons have no net electric charge, but the protons very much do. They are repelling each other frantically. This is not only true with helium, but with every other element on the periodic table that has more than 1 proton in the nucleus. The protons are all electrically repelling each other. In other words, protons are repelling each other in every element except hydrogen. If the protons in the nucleus are repelling each other electrically, then what is preventing the nucleus from flying apart? In order for the nucleus to stay together, there must be some other force pulling the protons, and it turns out the neutrons, together in order to balance against the electric repulsion. In other words, there must be some attractive force in the nucleus that is strong enough to overcome electric repulsion. We call this force the strong force, and with good reason. It is the strongest force known to physics. Yes, inside the nucleus, the electric force is trying desperately to make those protons fly away from each other, but the strong force prevents that from happening. The strong force holds the protons and the neutrons together. Although the strong force is very strong, it also has very short range. It can't reach outside the nucleus. That's why nuclei are small. If the nucleus is too big, the strong force can't reach from one side of the nucleus to the other. In other words, the strong force can't hold a very large nucleus together. The electric force destroys it. So the size of a nucleus is limited by the range of the strong force. It turns out that all the forces known to physics can be categorized into 4 fundamental forces. The strongest fundamental force is the strong force. It holds nuclei together, but, as we said, also has a short reach. It can't do anything outside the nucleus. The second strongest force is the electromagnetic force. This includes both electricity and magnetism, but is also responsible for friction and the normal force, that is, the force that prevents you from falling through the chair and the floor. The electromagnetic force theoretically has an infinite range. It could, under the right circumstances, attract or repel 2 charges on different planets. But in nature, it doesn't do that, because the electromagnetic force only applies to particles with electric charge, like protons and neutrons, and while the universe is filled with such particles on small scales, the universe is almost, or maybe exactly, electrically neutral on the large scale. Large objects, like planets and stars, are electrically neutral. So the electromagnetic force, while it is important in astrophysics, isn't nearly as important as gravity. Earth's orbit around the sun isn't due to electric attraction, but to gravitational attraction, because the positive and negative electric charges on Earth are all canceling each other out. The third strongest force in nature is called the weak force. Under some circumstances, it can cause quarks to decay. In so doing, it can turn a proton into a neutron. And the weakest of the 4 forces is gravity. Now, to call gravity a force is to take the Newtonian approach. Remember, according to Einstein's theory of general relativity, gravity isn't a force at all, but rather the curvature of space-time. But for the purposes of this lecture, we will take the Newtonian view and call gravity a force. It is the weakest force because it takes something very massive to have a noticeable effect. It takes a body the mass and size of the entire Earth to give you your weight. Like electricity, gravity has an infinite range, but unlike electricity, there are no opposing charges in gravity. There are no positive and negative gravitational charges that cancel each other out on large scales, like electric charges do. So while the electromagnetic force is weak on the scale of, say, the solar system, because the protons and the electrons cancel each other's charges out, Gravity dominates on large scales. It is gravity, not electricity, that keeps you bound to the Earth, that keeps the Earth in orbit around the Sun, and the Sun in orbit around the Milky Way galaxy. Because gravity, weak though it is cumulative. All the mass in the galaxy combines to keep the Sun in orbit around the galaxy. So gravity has a very long reach. What does the strength of forces have to do with nuclear physics? A chemical reaction such as fire uses the electromagnetic force to release energy. A nuclear reaction uses the strong force and sometimes the weak force as well. Well, the strong force is a hell of a lot stronger than the electromagnetic force. So you can extract a hell of a lot more energy from nuclear reactions than from chemical reactions. On the left is a chemical reaction, fire. On the right is a nuclear reaction, a hydrogen bomb. Nukes win. The two types of nuclear reaction we'll discuss in this class are fission, the breaking apart of large nuclei, and fusion, the joining together of small nuclei. Nuclear fission is when a large nucleus like uranium splits into two smaller ones, releasing energy. In nature, a mined rock of uranium, an ore of uranium, will contain at least two isotopes of uranium, U-235 and U-238. A U-235 nucleus just has 235 total protons and neutrons, while a U-238 nucleus has 238 total protons and neutrons. U-238 is by far the most abundant isotope and is used in nuclear power plants like the one in Russellville. U-235, on the other hand, is used in making nuclear bombs. So-called enriched uranium is when the power plant isotope U-238 has been removed, leaving only the nuclear bomb isotope U-235. But even a rock of pure U-235 won't explode on its own. In order for that to happen, the nucleus must capture an electron to form U-236, which very quickly then splits apart into barium, krypton, and crucially, 3 more neutrons. These 3 neutrons then act like bullets, smashing into other uranium nuclei and causing them to break apart as well, releasing even more energy. So if, and only if, the U-235 nuclei are packed densely enough that some of the neutron bullets will actually hit other nuclei instead of missing their targets and fly away, then each splitting nucleus triggers another splitting nucleus, which triggers another and another and another in an unstoppable series of reactions, a chain reaction, a nuclear bomb. Large nuclei, like uranium, release energy when they split apart. But small nuclei, like hydrogen, release energy the opposite way, by fusing together. As powerful as uranium fission is, hydrogen fusion is even more powerful. Hydrogen fusion powers the sun and nearly all stars. It also powers the most powerful class of nuclear weapons, the hydrogen bomb. It may, in the coming decades, also be used in power plants, but the engineering problems for that are formidable. Scientists around the world are racing to build fusion power plants, but they are still in the development stage. You'd be forgiven for thinking of our sun as a giant ball of fire, but if you put that on the test, you'll get it wrong. The sun is not on fire. Fire simply does not release enough energy to keep the sun shining for billions of years. If the sun were on fire, it would have burned out long ago, like a campfire. The sun is not powered by fire, but rather by nuclear fusion, turning hydrogen into helium. A hydrogen nucleus is simply a proton. Four protons combine to form a helium nucleus, and in the process, two of those protons flip into neutrons. Before we continue, we need to define a term, atomic mass unit, which is the approximate mass of one proton. It's a very small mass on the order of 10 to the minus 27 kilograms. A helium nucleus is made of two protons and two neutrons. If you add up the masses of those particles separately, they total about 4.03 AMU. However, when you combine them into one helium nucleus, their total mass is less than that, only about 4.00 AMU. A helium nucleus is therefore less massive than the sum of its parts, about 0.03 AMU less massive, to be precise. That mass was lost during nuclear fusion, so what happened to it? Remember that mass is a form of energy, so it can't be destroyed, it can only be converted to other forms. That's what Einstein's famous equation E equals mc squared means. A small amount of mass contains a very large amount of energy. When hydrogen fuses to form helium, a little bit of its mass is converted to other forms of energy, such as gamma rays, very high energy photons. And that energy eventually makes its way out into space as sunlight. 0.7% of hydrogen's mass is converted to other forms of energy during the nuclear fusion process. And that is why the sun shines. The sun is not on fire. The sun converts 400 metric tons of mass into sunlight every second. It's time for another vocabulary word, atomic number, which is the number of protons in an element. Hydrogen has atomic number 1, which means all hydrogen has one proton, no matter how many neutrons it has. Carbon has atomic number 6, which means all carbon has 6 protons, no matter how many neutrons it has. Atomic mass, then, is approximately the total number of protons and neutrons combined in a given nucleus. The atomic mass defines the isotope. All carbon has 6 protons, so the isotope carbon-12 has 6 protons plus 6 neutrons. 6 plus 6 is 12, for an atomic mass of about 12. The isotope carbon-14, on the other hand, still has 6 protons, otherwise it wouldn't be carbon. 6 protons plus 8 neutrons, for an atomic mass of 14. Now we can finally come around to radioactivity. Some isotopes are radioactive. A radioactive nucleus is one that spontaneously decays or changes into one or more other nuclei, releasing energy in the process. For example, most of the carbon in your body is carbon-12, which is not radioactive. However, a very small percentage of the carbon in your body is carbon-14, which is a radioactive isotope. Likewise, a small percentage of the potassium in bananas is potassium-40, which is a radioactive isotope. Both of the uranium isotopes we've discussed so far, U-235 and U-238, are radioactive. When a radioactive nucleus decays, it can release energy in the form of an alpha particle, or helium nucleus, a beta particle, or electron, a gamma ray, which is a high energy photon, or thermal energy. It can heat up its surroundings. A radioactive isotope has a half-life. This is the amount of time it takes for half of a given sample to decay. Some radioactive isotopes have very short half-lives, much less than 1 second, so they decay very quickly. While some isotopes have very long half-lives, billions of years or more, so they decay very slowly. So whatever the half-life of a particular isotope happens to be, after one half-life, half of the radioactive substance will have decayed. After 2 half-lives, half again, or 3/4 total, will have decayed. After 3 half-lives, half again, or 7/8 total, will have decayed, and so on. For example, living organisms have traces of carbon-14, which they take in through the air. Carbon-14 has a half-life of 5,730 years. So if we find a fossil with half of its carbon-14 intact, why, we know that fossil is around 5,730 years old. If a fossil has 1/4 of its carbon-14 intact, that means 3/4 of it has decayed, so it is 2 half-lives old, or 2 times 5,730, which is, I don't know, 11,460. Check me on that. Radioactive isotopes have a wide range of half-lives. Oxygen-24, for a random example, has a half-life of about 2 movie frames. Compare that with uranium-238 down here, which has a half-life of about 4.5 billion years, which is the age of the solar system. So radioactive decay, then, is a clock. We can use radioactive isotopes to measure how old things are. For example, potassium-40, what's in bananas and asteroids, decays into argon-40 with a known half-life, one that's been measured in laboratory. So by cracking open an asteroid and comparing the amount of potassium-40 to the amount of argon-40, we can tell how much of the potassium has decayed, which means we can tell how long the potassium has been decaying, which means we can tell the age of the asteroid. And since asteroids all appear to have about the same age, and they seem to have formed at the same time as our solar system, the age of the asteroids is a good approximation of the age of the solar system, and the asteroids all agree. The solar system is about 4.5 billion years old. Another example, carbon-14 is found in fossils. So by measuring the amount of carbon-14 that remains in a fossil, we can tell how much of the carbon-14 has decayed. In other words, we can tell how long the carbon-14 has been decaying. In other words, we can tell the age of the fossil. Our planet, Earth, is hot inside, and the deeper you go, the hotter it gets. The core of the Earth is about 12,000 degrees Fahrenheit. Why is it so hot? Partly because the Earth is big, so it traps heat inside it. About half the thermal energy inside the Earth today is left over from when the Earth formed, when huge asteroids, some the size of small planets, we call them planetesimals, were smashing into the Earth on a regular basis. But the other half of the thermal energy inside the Earth today comes from ongoing radioactive decay of elements like uranium, thorium, and potassium-40. Well, we made it through radioactivity, so let's do poetry. Say it with me. An atomic nucleus is made of nucleons, which are protons and neutrons. And we all feel like dorks knowing nucleons are made of quarks. When nuclei spontaneously decay, we call it radioactivity. I've waited my whole life to say it that way. When I say physics, you say rocks. Physics! Did you say it? Yeah, you did. Now, go do your lecture quiz right now while the lecture's still fresh. Go! See you next time.